Hello and welcome to this demo on working with Cluster Autoscaler add-on. I am Mahendra Mehra, your senior OCI instructor with Oracle University. In this demo, we'll be diving into the functionality of the Kubernetes Cluster Autoscaler, specifically focusing on its role as a cluster add-on. Let's dive in. During our demo, we'll be walking through a series of essential steps to effectively work with the Kubernetes Cluster Autoscaler add-on. To start with, we will be creating a dynamic group to allow nodes running the Kubernetes Cluster Autoscaler to manage node pools referenced in the Cluster Autoscaler add-on configuration. In the interest of time, I've already created the dynamic group. Now let me showcase what we have set up. I'll be transitioning to the OCI console. I've already logged into my OCI console. I'll take you to the dynamic groups page. I'll click on the hamburger menu. Go to Identity and Security and click on Domains. I'll select my root compartment here and go to the default domain. I'll select Dynamic Groups from the left menu. And here I've already created a dynamic group named Acme OKE Cluster Autoscaler Dynamic Group. I'll select it. As you can notice, this dynamic group is for all the instances running in the compartment with the OCID as given on the screen, and this is the OCID of my compartment CTD OKE. Let's head back to the slide deck. The next step is to create policy to allow worker nodes to manage node pools. We have already created a dynamic group for all our worker nodes running in the CTD OKE compartment. Now we'll be creating the policy to allow these worker nodes, or indirectly the dynamic group, to manage all the node pools within the compartment CTD OKE. Again, in the interest of time, I've already set those policies. Let me show it to you. I'll click on the hamburger menu, go to Identity and Security, and click on Policies. I'll select the parent compartment for my CTD OKE compartment, which is Mahendra. And here I've already set up the policies for our dynamic group. I'll click on the policy. These are the policies that you must set to allow your worker nodes to manage the node pools. The policy is to allow dynamic group, the name of our dynamic group, which is Acme OKE Cluster Autoscaler Dynamic Group, to manage cluster node pools in compartment CTD OKE. The other set of policies are to manage instance family, use subnets, read virtual network family, use VNix, and inspect compartments in the compartment CTD OKE. Next step is to enable the add-on on the Kubernetes cluster, where we want to set up the cluster autoscaler. I'll head back to the OCI console and go to the Kubernetes service page. Let me select the navigation menu, click on Developer Services and click on Kubernetes Clusters. I'll select the CTD OKE compartment, and here and from the list of clusters in my CTD OKE compartment, I'll be selecting the OCI OKE CA demo cluster for this demonstration. On the cluster, I'll scroll down to the resources section and click on add-ons. And currently we don't have the cluster autoscaler add-on enabled. I'll click on manage add-ons button. And if we scroll down, we have the cluster autoscaler add-on available, which is currently disabled. I'll select this option and I'll check the enable cluster autoscaler add-on. We get to choose from the two options. One is the automatic updates, where Oracle manages the automatic updates of this add-on on your cluster, or else we can opt for choose a version option, where we select the version manually from the drop down. There are 3 versions available for the current cluster version. I'll stick to the automatic updates. Now let's populate the parameters for the cluster autoscaler add-on. The first parameter we'll populate is nodes. Nodes parameter basically specifies the node pool to automatically resize, and to specify the minimum and maximum number of nodes in each node pool, we must use the following format. The format is minimum number of nodes, separated by maximum number of nodes, and separated by the node pools OCID. And if we have multiple node pools to manage through the cluster autoscaler, then in that case we must use comma separation and specify the same format for the other node pools in your Kubernetes cluster. So this is the format in which we specify the value for our nodes parameter, where the minimum nodes value is the number of nodes allowed in the node pool. The Kubernetes autoscaler will not reduce the number of nodes below this number. In our case, I've specified it as 2. And the max nodes value is the maximum number of nodes allowed in the node pool, where the Kubernetes cluster autoscaler will not increase the number of nodes above this number. In our case, it is set to 5. And then here I've specified the OCID of our node pool, which the Kubernetes cluster autoscaler will manage. Now, how do you get the node pool's OCID? You go to the cluster's detail page. I'll select the cluster first and go to the node pools section. Click on the node pool name and copy the node pool OCID from the node pools detail page. I'll go back to the notepad file and replace this OCID with the OCID of our node pool. Copy the entire string and go back to the first tab and paste the value in this box. I'll go ahead and configure the next parameter, which is the number of replicas. Remember from the lesson that we must always define multiple replicas for the Kubernetes cluster autoscaler deployment, which is why I'll set it to 3. I'll add another parameter to the Kubernetes cluster autoscaler configuration, which is maximum node provision time, and I'll set it to 25 minutes. I'll go ahead and click on Save Changes. And as we can observe, the cluster autoscaler add-on is now enabled. I'll click on Close. And the entry for the cluster autoscaler is now present in the add-ons section, and the status says ready. Now, once the cluster autoscaler add-on is enabled, the next step is to verify the autoscaler status. To view the status of the Kubernetes cluster autoscaler pods, we can use the kubectl get pods command, and these pods run within the kube system namespace. I'll head back to the OCI console. On the next tab, I've already opened up the Cloud Shell terminal. I have already set up the cluster access to our Kubernetes cluster. I'll run the kubectl get nodes command. The cluster that I'm using for demonstration has one node pool running 2 worker nodes within it. Confirm the same. If I go to the node pools section, there is one node pool running 2 worker nodes within it. Now, to view the status of Kubernetes cluster autoscaler pods and observe progress of the deployment, we can run the kubectl get pods command. The command is kubectl get pods -n kube system. The cluster autoscaler pods run within the kube system namespace, and we are piping it to the grep operator to select only those pods that are titled as cluster autoscaler. I'll go ahead and hit enter. And if you recollect, we had set number of replicas to 3 for our cluster autoscaler, which is why we can see 3 pods of cluster autoscaler running in our Kubernetes cluster. Now, to view the Kubernetes cluster autoscaler logs, just to confirm that the add-on was successfully deployed and is currently monitoring the workload of the node pool that we had defined within the configuration, we must run the kubectl logs command. The command is kubectl -n kube system logs, and we are fetching the logs for the deployment of our Kubernetes cluster autoscaler. I'll go ahead and hit enter. And from the output, we can confirm that the Kubernetes cluster autoscaler is successfully deployed and is currently monitoring the workload of our node pool. I hope you're enjoying the demo so far. See you in the next one. Thank you for watching. Hello and welcome to this lesson on Kubernetes Metrics Server Overview. I am Mahendra Mehra, your senior OCI instructor with Oracle University. Let's get started. Picture the metrics server as the central hub aggregating resource usage data from each worker node's kubelet. This valuable data is then exposed through the Kubernetes metrics API. Now let's explore the crucial connections extending from the metrics server in our diagram. This represents the vital links to other Kubernetes add-ons. The horizontal pod autoscaler. It utilizes this data to dynamically adjust the number of pods in a deployment, ensuring optimal resource usage. On the other hand, the vertical pod autoscaler, also known as VPA, leverages the metrics server to fine-tune the resource request and limits for containers running in a deployment pod. Let's highlight two critical aspects of the Kubernetes metrics server. First, its versatility, compatible with both managed node pools and virtual node pools, offering you choices in deployment. Second, essential to understand that the metrics server is purpose-built for autoscaling. While it excels in this role, it's not recommended for forwarding metrics to monitoring solutions or serving as a standalone source for monitoring metrics. With this, we come to the end of this lesson where we quickly got an overview about the Kubernetes metrics server. I hope you found this lesson useful. See you in the next one. Thank you for watching. Hello and welcome to this demo on deploying the Kubernetes metrics server on a cluster using kubectl. I am Mahendra Mehra, your senior OCI instructor at Oracle University. Let's get started. Well, let's look at the steps required to deploy the Kubernetes metrics server. Firstly, we must set up the cluster access using the kubeconfig file. For this demonstration, I've created a Kubernetes cluster named OKE metrics server demo. I'll use this for our demonstration. I'll go ahead and click on the cluster name. To set up the cluster access, I'm on my cluster details page and I'll click on the access cluster button. I'll copy the command provided for the Cloud Shell access. I'll go to the next tab where I've already opened up the Cloud Shell terminal and paste the command, hit enter, and the cluster access has been set up. I'll run the kubectl get nodes command. Well, it has returned the worker nodes running in our Kubernetes cluster. I'll close this window, go to the node pools section, click on the pool name and confirm the IPs which are ending with 198, 188 and 71 are the same that has been retrieved when we ran the kubectl get nodes command. This is just to verify that I'm connected to the right Kubernetes cluster. Well, this node pool is a managed node pool. Remember that the Kubernetes metrics server can also be installed on virtual node pools. For this demonstration, I'll stick to managed node pools. Now the next step is if your Oracle Cloud Infrastructure user is a tenancy administrator or cluster administrator, we can skip this step. But if your OCI user is not a tenancy administrator or cluster administrator, then you must ask your tenancy administrator or cluster administrator to grant the user the Kubernetes RBAC cluster admin cluster role on the cluster. And to do that, you can use the kubectl create cluster role binding command, specify the name to the binding and set the cluster role flag to cluster admin. Also specify the user flag and provide the user's OCID. In our case, the user using which I'm running this demonstration is already an administrator. So I'll skip this step. The user OCID is available under the user's profile menu. You can click on the profile menu on the top right and click on my profile. And under the user information tab, you can simply copy the OCID and use it in the command. Now, if you are going to deploy the Kubernetes metrics server on a cluster with managed node pools, deploy the Kubernetes metrics server by entering the following command in the terminal. We should use the kubectl apply command and use the URL as given on the screen. But remember that the version number is the Kubernetes metrics server version that we want to deploy. For example, version 0.6.1. But note that since the Kubernetes metrics server is being actively developed, the version number to specify will change over time. And to find out the currently available version, you should visit the GitHub URL, which is this. As you can see from the URL, the current Kubernetes metrics server version is 0.6.4. You can use this command to set up the Kubernetes metrics server on our managed node pool. I'll copy this command and head back to the Cloud Shell terminal and paste the command here. I'll go ahead and hit enter. Well, all the required resources have been created for the Kubernetes metrics server. Now we must confirm that the Kubernetes metrics server has been deployed successfully and is available. To confirm the same, we can use the kubectl get deployment metric-server command and specify the namespace as kube-system. I'll go ahead and hit enter. And as we can notice, the metrics server is up and running. And like I mentioned, that you can install Kubernetes metrics server on a cluster with virtual node pools also. And in order to do so, you must go to the following URL in the browser and download the manifest file, that is components.yaml, to your local machine. Remember, you must provide the latest version number for your Kubernetes metrics server. Now, once you download the components.yaml manifest, you must remove the liveness probe and readiness probe section from the manifest of the metrics server deployment. I have already downloaded the components.yaml manifest. Let me bring it up for you. This is the component.yaml manifest used to deploy the Kubernetes metrics server. Scroll down and locate the liveness probe and readiness probe section. As you can notice on the screen, this is the liveness probe section that you must delete, as well as the readiness probe section. Save the components.yaml manifest file after editing on your local machine and run the kubectl apply command to deploy the Kubernetes metrics server on your Kubernetes cluster running virtual node pools. To confirm that the Kubernetes metrics server has been deployed successfully and is available, you must enter the command kubectl get deployment metrics server and specify the namespace by using -n. The namespace is kube system. The output will confirm whether the metrics server is ready or not. As in our case on the managed node pool, the metrics server was successfully deployed. With this, we come to the end of this demo where we successfully deployed the Kubernetes metrics server on the container engine for Kubernetes cluster using kubectl. I hope you found this demo interesting. See you in the next one. Thank you for watching. Hello and welcome to this lesson on Kubernetes Horizontal Pod Autoscaler. Let's get started. Kubernetes Horizontal Pod Autoscaler is a powerful tool for automating pod scaling in your Kubernetes cluster. To unleash its potential, you'll need to install a metrics source such as the Kubernetes metrics server in your cluster. As you engage with the Horizontal Pod Autoscaler, you gain the ability to dynamically adjust the number of pods in your deployments, replication controllers, replica sets, or stateful sets. This adjustment is intelligently driven by factors like CPU, memory utilization, or other metrics, allowing your applications to seamlessly scale out during periods of high demand or scale in when resources are no longer needed. Adding precision to your scaling strategy, you can set target metric percentages for the horizontal pod autoscaler to meet when scaling your applications. The flexibility doesn't end here. If your scaling needs extend beyond CPU and memory utilization, alternative implementations of the Kubernetes metrics API support scaling based on custom metrics. While the horizontal pod autoscaler brings automation, it's important to note that manual scaling options are also available. You can manually scale applications by updating manifest files without relying on the horizontal pod autoscaler. Whether you are working with managed node pools or virtual node pools, the Kubernetes horizontal pod autoscaler seamlessly integrates into your Kubernetes environment, providing a versatile and efficient scaling solution. Stay tuned as we explore the hands-on demonstration, unraveling the functionalities and configurations of the horizontal pod autoscaler in Container Engine for Kubernetes in our next video. Thank you for watching. Hello and welcome to this demonstration on working with the horizontal pod autoscaler, a powerful tool that enables automatic scaling of the number of pods in response to different workloads. Let's get started. There are different steps in which we'll be performing this demonstration. For the horizontal pod autoscaler to work, we need to install Kubernetes metrics server. The first step would be to verify that the Kubernetes metrics server has been installed on the cluster or not. I will head to the OCI console, and in the OKE cluster that we are using for this demonstration, let's quickly check the metrics server status. I'll first visit the cluster that I'll be using for this demonstration. I'll click on the Kubernetes clusters link from the recently visited section. OKE metrics server demo is the cluster we'll be using for this demo. I'll click on the link. This is a cluster running with one managed node pool. And the managed node pool is operating with 3 worker nodes. On a separate tab, I have opened up the Cloud Shell terminal, and here I'll run the command kubectl-n kubesystem get deployment/metrics server. The output of this command will confirm the installation of metrics server on this cluster. Well, the output confirms that the metrics server has been installed on this cluster. As we can see from the ready column, there's one pod of metrics server running on the Kubernetes cluster. We have already covered installation of metrics server on an OKE cluster in our previous demo. To demonstrate a horizontal pod autoscaler, we will first start a deployment that runs a container using the horizontal pod autoscaler example image and expose it as a service using a manifest file. To deploy the sample application, we can run kubectl apply -f and the URL to that sample application, which is available as part of the Kubernetes examples. But in our case, I've downloaded the PHP Apache manifest on our local machine. I'll open up the manifest for you. Let me clear the screen and navigate to my examples directory. Here is the manifest that I have downloaded from the same URL I showed you in the earlier command. Now I'll open up the manifest file. Well, from the manifest file, it's clear that it's creating a deployment with the name PHP Apache. And from the containers section, we can confirm that it's pulling an image from the registry.k8s.io repository. And the name of the image is HPA example. And the container port 80 has been exposed. Now under the resources section, make a note that the CPU limit has been set to 500 millicores, which ensures that the container will never use more than 500 millicores or half of a core. And the request allowance is set to 200 millicore, which allows the container to use 200 millicores of CPU resources or 1/5 of a core. At the bottom, we have the service section defined to expose the deployment PHP Apache using cluster IP on port 80. We'll close this manifest file and go ahead and deploy this manifest on our Kubernetes cluster using the kubectl create command. I'll hit enter. Well, the deployment and the service PHP Apache has been created. Now if I run kubectl get all command, you can notice that the PHP Apache pod is up and running, as well as the service PHP Apache of type cluster IP is up and running. Pod PHP Apache is part of the deployment PHP Apache with the replica set where the desired count for the pod is set to 1. Now the next step is to create a horizontal pod autoscaler resource that will scale based on CPU utilization. I'll clear the screen, and to run the autoscaler I'll use the command kubectl autoscale deployment and the name of deployment, which is PHP Apache, and I'm setting the CPU percentage to 50 and the min count is set to 1, whereas the max count is set to 10. With the help of this command, I'll create a horizontal pod autoscaler resource to maintain a minimum of 1 and maximum of 10 replicas and an average CPU utilization of 50%. I'll go ahead and hit enter, and the output says horizontal pod autoscaler PHP Apache has been autoscaled. What this autoscaler would do is it would maintain a minimum of 1 and maximum of 10 replicas of the previously created pods controlled by the Apache web server deployment. It increases and decreases the number of replicas of the deployment to maintain an average CPU utilization of 50% across all pods. Remember, if the average CPU utilization falls below 50%, the horizontal pod autoscaler will try to reduce the number of pods in the deployment to the minimum, which in this case is 1. And if the average CPU utilization goes above 50%, the horizontal pod autoscaler will try to increase the number of pods in the deployment to the maximum value. And in this case, we have set it to 10. Let's check the current status of horizontal pod autoscaler by entering the kubectl get HPA command. I will hit enter. The output of the kubectl get HPA command shows the current status. The target column shows the average CPU utilization across all pods controlled by the Apache web server deployment. Now, since there are no traffic being sent to the server, the output shows the current CPU utilization as 0% compared to the target utilization of 50%. Next step is to generate load. We will see how the autoscaler reacts to increased load. And to do this, we will start a different pod to act as a client. The container within the client pod runs in an infinite loop and sends queries to the PHP Apache service. Let's head back to the OCI console and start generating load. Using the kubectl get svc command, I'll grab the cluster IP address of the PHP Apache service. Now I will use the kubectl run command to generate load using the client pod that is running busybox image. And the script here is executing while loop where we are continuously sending traffic to the cluster IP, which is running the service that is exposing the PHP Apache deployment. I'll go ahead and hit enter. As you can notice, the requests are being sent to the cluster IP that is exposing our PHP Apache deployment. Now that we have started generating load, it's time to view the scaling operation in action. Let's head back to the OCI console. I will switch to a new terminal and run the kubectl get HPA command. I'll supply the watch flag. We'll notice that the CPU utilization across all pods controlled by the Apache web server deployment is above 50% at the start, and the horizontal pod autoscaler is trying to bring it to 50%, for which it is trying to create new replicas of the pod running the PHP Apache web server. From the output, we can notice that the horizontal pod autoscaler has resized the deployment from 1 replica to 5 replicas and then to 7 in order to get the utilization target of 50%. Make a note that one might see different numbers depending on how long they wait before running the command. For us, it has scaled to 7 replicas where it could meet the utilization parameter of maintaining 50% across all pods. I'll quit the command here and clear the screen. Now to verify that the deployment has been scaled out, I'll run the command kubectl get deployment. And we can observe that the PHP Apache deployment has been scaled out and there are 7 pods running for the PHP Apache web server. Now I'll go to the previous tab and stop generating the load. I'll press Ctrl C here and this has stopped generating the load. I'll go back to the next tab and we will see the status of horizontal pod autoscaler after we have stopped generating the load. Run the command kubectl get HPA and provide the deployment name, that is PHP Apache. Hit enter. I'll use the watch flag here. We'll notice that the CPU utilization has reduced to 0%. However, we can still see 7 replicas in the deployment. Just a note that you will see different numbers depending on how long you wait before running the kubectl get HPA command after the load generation has stopped. Also be aware that it will take some time for the replica count to reduce to 1. 5 minutes is the default time frame for scaling in. Notice that after a while the horizontal pod autoscaler is trying to scale in the number of pods as the CPU utilization has decreased. Now we can notice that the number of pods running for the PHP Apache deployment is reduced to 1. I'll quit this command and we will run the kubectl get deployment command. And we can confirm from the output that the number of pods have reduced from 7 to 1 after the load generation was stopped. Now to perform cleanup, I'll use the kubectl delete command to delete the horizontal pod autoscaler. I'll go ahead and hit enter. And the output says the PHP Apache horizontal pod autoscaler was deleted. With this, we come to the end of this demo where we saw in action how the Kubernetes horizontal pod autoscaler automatically scales the number of pods on a container engine for Kubernetes cluster. I hope you found this demo interesting. See you in the next one. Thank you for watching. Hello and welcome to this lesson on Kubernetes vertical pod autoscaler. Let's get started. Firstly, the vertical pod autoscaler automates the adjustment of resource requests and limits for containers in your deployment pods, providing an intelligent and automated solution for optimal resource utilization. This tool enhances your cluster's resource efficiency by dynamically setting requests based on pod usage, ensuring that the appropriate resource amounts are available for each pod. It also maintains the specified ratios between limits and requests, aligning within the container's initial configurations. For efficient scaling, the vertical pod autoscaler scales down pods that over-request resources, analyzing their historical resource usage. On the flip side, it scales up pods that under-request resources, adapting to their usage patterns over time. The vertical pod autoscaler operates through 3 key components. The recommender monitors current and past resource consumption, providing recommended CPU and memory request values. The updater identifies pods with incorrect resources, deletes them, and recreates them with updated request values. And the admission plugin sets correct resource requests on new pods created or recreated by their controller. To configure the vertical pod autoscaler, you'll use the vertical pod autoscaler custom resource definition object. This enables you to specify the pods for vertical autoscaling and define resource recommendations as needed. It's important to note that the vertical pod autoscaler requires the installation of a metric source in the cluster, such as the Kubernetes metric server, to function properly. This dependency ensures accurate monitoring and adjustment of resources. Stay tuned as we explore hands-on demonstrations unraveling the functionalities and configurations of the vertical pod autoscaler in Container Engine for Kubernetes. I hope you found this video useful. Thank you for watching. Welcome to our lesson on upgrading clusters to newer Kubernetes versions. In this video, we'll explore the process of upgrading your Kubernetes version on control plane nodes and worker nodes within an OKE cluster. Let's get started. When you create a new Kubernetes cluster by using Container Engine for Kubernetes, you have the flexibility to specify the version of Kubernetes for both the control plane nodes and the worker nodes in the cluster data plane. Notably, within a single node pool, you can even have different worker nodes running different versions of Kubernetes. Additionally, if your cluster comprises multiple node pools, each node pool can operate on its own distinct version of Kubernetes. Let's explore these customization options further. Let's explore the dynamic world of Kubernetes versions. Kubernetes project frequently releases new versions, each bringing a mix of fresh features, updates, and bug fixes. These versions are uniquely identified by a three-part format: x.y.z, where X represents a major release, Y is a minor release, and Z signifies a patch release. For instance, we might have a version like 1.27.2. It's worth noting that there is a relationship between the versions on worker nodes and control plane nodes. The Kubernetes version on the worker nodes can lag behind the control plane nodes by up to 2 versions or 3 versions starting from Kubernetes version 1.28. However, exceeding this lag renders the version incompatible. As shown in the graphics, if the control plane node is running on version 1.27.2 and the worker nodes are running on version 1.27, which is similar to the one running on control plane, or 2 versions behind, which is 1.26 and 1.25, they are compatible. But if the gap increases by 2, as shown in the graphics here, where the version of the worker node is 1.24.1, in this case, they become incompatible. Also, a point to note is that the versions on worker nodes must not be more recent than the versions on the control plane nodes. As shown in the graphics here, if your worker node is running version 1.28 and the control plane is running version 1.27, in this case, they both become incompatible. A worker node should never be running version greater than your control plane node. Let's navigate through the key points. Firstly, Kubernetes embraces version diversity, allowing control plane nodes and worker nodes to gracefully run different versions, all within the bounds of the Kubernetes version SKU support policy. Now, the upgrade journey begins. Upgrading control plane nodes involves elevating the entire cluster to a new Kubernetes version. During this orchestrated upgrade, control plane nodes running older versions undergo an automatic and graceful transformation to align with the upgraded cluster. One notable feature is the zero downtime during the upgrade process. Thanks to the high availability distribution of control plane nodes, this ensures uninterrupted service availability for your applications. Post-upgrade, you have flexibility. Create new node pools with your worker nodes sporting the latest version or continue with existing ones provided they are compatible with the upgraded control plane version. In conclusion, upgrading control plane nodes in Kubernetes is a meticulous and smooth operation, providing you with flexibility and ensuring minimal disruption to your running applications. I trust you found this lesson insightful. See you in the next one, and thank you for watching. Hello and welcome to this short demo on upgrading clusters to new Kubernetes versions. I am Mahendra Mehra, your senior OCI instructor at Oracle University. Let's get started. I'll transition to the OCI console. I'm already logged into my OCI console and I'll go to the Kubernetes clusters service page. I'll go through the recently visited links. The cluster which I'll be upgrading is the OKE public demo 2 cluster. I'll select this cluster. Now, as we discussed in the lesson, if a newer Kubernetes version than the one running on the control plane nodes in the current cluster is available, the new Kubernetes version available button is enabled at the top of the cluster's details page. Now, to upgrade the control plane nodes to a newer version, I'll click on this button. And any new information regarding the current update is provided on this window. As you can notice, the pod security policies will be disabled from version 1.25 onwards. And also, if you upgrade your cluster's control plane, you cannot downgrade it. So it's always recommended that you test the applications deployed on the cluster to see if they are compatible with the newer Kubernetes version. Now, to upgrade the cluster control plane, I'll select the drop down from the Kubernetes version field, and as you can notice, we have the upgraded version available, which is version 1.28.2. I'll select this version and click on upgrade. Once we click on upgrade, the cluster will enter in updating state. As you can see on the screen, the cluster is now in the updating state. We can check that through the work request section. As you can notice, the cluster update operation is in progress. In the meanwhile, a quick information that when you upgrade the Kubernetes version running on the control plane nodes, the virtual nodes in every virtual node pool in the cluster are automatically upgraded to that Kubernetes version. This cluster is running managed node pools, but if your cluster is running virtual node pools, it's an important piece of information to have. Notice the current Kubernetes version is 1.27.2. This will change after the update process to 1.28.2. Well, after some approximately 7 to 8 minutes, the Kubernetes control plane has been upgraded to version 1.28.2. Once the Kubernetes version running on the control plane node is upgraded, the new Kubernetes version appears as an option when you are defining new node pools for the cluster. Let me show this to you in action. I'll go to the node pools section, click on add node pool. And if you notice, the worker nodes in the node pool are still running on the previous version, which is 1.27.2. But if we go ahead and create a new node pool now, we will have the option to choose the latest version. And if you notice in the version field, we can choose from all of these versions that are available. And as discussed in the lesson, from version 1.28 onwards, the worker nodes can lag by 3 older versions, which is why we have the option to choose Kubernetes version up till version 1.25.4. I'll click on cancel. We can also edit the properties of our existing node pool so that any new node added to the existing node pool can run on the latest Kubernetes version. I'll click on the existing node pool, and here I'll click on the edit button. This opens up the edit node pool page, and under the versions field, from the drop down, we can select the latest version, that is version 1.28.2, which is the current cluster version. And as the information reads, it says node added to this node pool will run the upgraded version, which means any new nodes added to this node pool will be running Kubernetes version 1.28.2. For instance, if I add a new worker node to this node pool by increasing the node count to 4 and click on Save Changes, the node pool has gone into updating state. And in some time, we will see a new node entry here under the nodes section, which will have the Kubernetes version running 1.28.2. Well, as you can see, the node entry is created. Currently, it's in the creating state, but we can observe that the version running on the worker node is 1.28.2, which is one version ahead as compared to the Kubernetes version running on the previous worker nodes in the same node pool. After a while, our new node is now in the ready condition and in an active state, running the Kubernetes version 1.28.2. With this, we come to the end of this demo where we saw how to upgrade the Kubernetes clusters control plane node in OCI Container Engine for Kubernetes. I hope you found this demo useful. See you in the next one. Thank you for watching.